Okay, so this is the second video for chapter 11, and we're just going to finish up these PowerPoint notes and talk about some of the properties that are affected by our IMFs, all right? So we've already looked at boiling point. Melting point is similarly affected, but now we're going to look at viscosity, surface tension, and capillary action, and then we're going to talk about a couple other things like heating curves and phase changes, all right? So let's jump in. Viscosity is the measure of resistance to flow. So high viscosity is high resistance to flow. Low viscosity is low resistance to flow. Okay, so water would be less viscous than molasses. That's a way to think about it. We often use viscosity in order to rate oils that we might use in an engine. So if you see like SAE 40 or SAE 10, the 10 is the viscosity number. And so that lower viscosity number means it's going to pour faster. Now, viscosity increases with stronger intermolecular forces. And that makes sense, right? The greater the intermolecular force, the harder it is for the molecules to slide past each other, right? Viscosity is also going to decrease as temperature increases, because as the temperature increases, the kinetic energy of the molecules starts to overcome that force of attraction. If you wanted to pour molasses, right, the easiest thing to do would be able to, you take your jar of molasses and you stick it in hot water for a little while and you heat the molasses up, and then you try to pour it. It pours much quicker than if you try to pour cold molasses. All right, so that's viscosity. Viscosity increases with stronger intermolecular forces. Surface tension is the second one we're going to look at. You probably talked about, or I know you talked about surface tension in first year chem. I also know that you discuss it in biology. And basically, surface tension kind of gives water this skin, this layer on the outside edge of the molecules that you can press on just a little bit and it won't give. And the reason for that is there are all these extra inward forces that can be dispersed by the molecules inside. So, in the case of the water strider here, its foot presses down on these water molecules and it disperses that pressure to the surrounding water molecules and gives it this surface tension. Okay. Now, cohesion and adhesion are very, similar to surface area, right? Because if you're binding similar molecules to one another, we call that cohesion. Okay, that's intermolecular force. If you are binding a substance to another surface, it's called adhesive force. Now, cohesion is what we would use to explain surface tension, right? So if I go back here and I look, I have similar molecules, right? They're all water molecules. They're binding to each other, so they're cohesive. And that cohesion, more intermolecular force, right? Greater cohesion is what allows the water strider here to stand on the water. Cohesion and adhesion, if you put them together, give you something called capillary action. So what is capillary action? Well, capillary action is when a liquid starts to climb a really narrow tube on its own. It's like you don't have to do anything, it just happens. So the way that we explain that is pretty simple. Adhesive forces attract the liquid to the tube itself. Cohesive forces attract the liquid to itself. So water, all right, is a great example of a substance that demonstrates capillary action. We see it in the meniscus when we try to read, a graduated cylinder, because it looks like the water is climbing the walls of the graduated cylinder. We also see it in this picture in the test tube. And when we compare water to something like mercury, what has really strong cohesive, interactions with itself, but it doesn't form cohesive interactions with the glass. So if we zoom in here to the, molecular view, you can see that all of these molecules are, somewhat attracted to each other, and they're forming these bonds, all right, these little forces of attraction. And there's nothing between the mercury and the glass. And so you get this shape of a meniscus, right? But in water molecules, here again is our glass wall. So this is our glass on this side. And you can see, where'd my other S go? There we go. All these little red dots, right, all these forms of attraction, and that gives us this shape meniscus. So if we see the concave meniscus that water has, then we can, surmise, okay, there are strong intermolecular forces of attraction between whatever the substance is in the test tube and the glass wall of the test tube. On the other hand, if we see this convex mercury-shaped tube here where we have the dome top, then we can say, all right, well, there's not really an intermolecular force at play between whatever's in the test tube and the glass wall. So let's switch gears a little bit. Let's look at phase changes, all right? Now, phase changes are something that we talked about last year. We're going to go into a little bit more depth right now with that, and we're going to look at them more in terms of energy. Now, again, whenever there's a phase change, we have to overcome the intermolecular forces of attraction that are at play in order to affect that phase change. So greater forces of intermolecular attraction are going to drive up the amount of energy that's required in the system in order to get that phase change to occur. Now, the phase changes that we're talking about here are going to be melting, freezing, vaporization, condensation, sublimation, and deposition, all right? Make sure you know those. I'm sure you know most of them. The only one that may be kind of new to you is not vaporization, is deposition, and that's when you go directly from a gas to a solid. So if you need an example of that, frost is an example of that. So water vapor in the air is deposited directly onto glass, and that gives you what we call frost. That's going from the gas phase to the solid phase. So that would be an example of deposition. Now, the energy changes that are associated with changes of state, we define as the heat of fusion, the heat of vaporization, and the heat of sublimation. Now, the heat of fusion covers both melting and freezing. It just depends on the sign. Same thing is true of vaporization. It covers boiling and condensation. Sublimation is going to cover deposition and sublimation. All right? It's going to cover both. The sign is important. All right. So, and we'll see that on the next slide. But something that we should notice, all right, the heat of fusion is usually much less than the heat of vaporization, is usually much less than the heat of sublimation. You can see that really clearly here with mercury. All right. Now, a heating curve, something that we looked at in year one chemistry, is a great visual that goes or that's going to be tied in with these heats. So if I want to graph out the amount of heat versus the temperature, okay, remember heat is energy, the temperature is the molecular movement, right? If I want to graph out those things for the phase changes of some substance, I use a heating curve. Now, really, really, really important to understand this concept. And we'll see some math that backs this up. But when something is melting, when it's going from point B to point C here, there is no change in temperature. However, if we look at the final position on the heat compared to the initial energy or amount of heat, we know that the change in heat is equal to final minus initial. There is definitely a change in heat. Okay, so remember last year when we looked at Q equals MC delta T. If you go back and look in your notes, we talked a little bit about this last year. The heat, Q, this is the Q, all right? So when we're looking at heat added, all right, just like we did in thermochemistry and thermodynamics, heat is going to be Q. Temperature, or a change in temperature, is going to be T, or obviously delta T, all right? Now, we'll look at some math problems that involve these phase changes as far as how much energy is required there. But in order to do that, you're going to use heats of vaporization, heats of fusion, or heats of sublimation, whichever may be required. If you're melting, you're going to use heat of fusion, right? If you're boiling something, it'll be heat of vaporization. Now, in AP, we go a little bit further, right? Then, right here is F is where we stop with our year one chemistry. In AP, we're going to keep going. We're going to look at supercritical fluids. And a supercritical fluid is something that occurs when gas is liquefied due to an increase in pressure. So the temperature beyond which a gas cannot be compressed is called its critical temperature. If you look for the pressure that you need to compress a liquid at the critical temperature. That's called the critical pressure. Anything beyond that point is called a supercritical fluid. And supercritical fluids are really cool. I will, uh, I will encourage you to look up like a YouTube video of a supercritical fluid. They're pretty interesting. Your book has a little blurb about them. Read that little blurb. I don't know that you would ever get a math problem on the AP test about a supercritical fluid. I'm not concerned about that. Make sure you understand the definition and you understand the fact that the behavior of the gas changes when it is a supercritical fluid, all right? Now, vapor pressure is something else that we need to look at if we're going to talk about intermolecular forces and we're going to talk about liquids and phase changes and all that jazz. So if we think way back to these Boltzmann graphs that we looked at earlier in the year, and we talk about when we talked about like root mean speed and stuff like that, or root mean square speed. At higher temperatures, all right, there is a greater distribution of kinetic energy amongst our molecules. So vapor pressure is what's the best definition for vapor pressure? Let me go forward a slide here. So, nope, went too far. All right. So vapor pressure is the pressure that's exerted by the molecules of a liquid as they kind of phase up into a gas. Now, eventually, there's going to be a dynamic equilibrium reached between the liquid and the vapor, and in which you're evaporating at the same rate you're condensing, and that pressure that you're left with is going to be your vapor pressure. So it's the fact that some molecules at the very edge, right at the interface of a liquid, have enough kinetic energy to overcome those forces of attraction and to vaporize. All right, so if you look at different temperatures and the vapor pressure, you'll find that the vapor pressure, that the number of molecules that are becoming a vapor is going to increase, right, with the increase in temperature. So if we look at the first graph here with the blue line, only the shaded blue area are the molecules that are able to break free of the liquid and become a gas. If you have a higher temperature, right, the curve kind of flattens and shifts to the right. And so now you have the red and the blue area all under that curve, right? So this whole area, okay, is the number of molecules that can escape. Now, what might we, need to know about vapor pressure for? Well, the boiling point of a liquid is the temperature at which the vapor pressure equals the atmospheric pressure. And for the normal boiling point, we always use 760 torr. Now, that's a really useful piece of information to know because vapor pressure is really easy to graph. And so if you know the vapor pressure, you can then determine whatever the boiling point would be at different temperatures. So that's what we would use this for. Now, there's also a relationship called the Clausius-Clayperon equation that posits the natural log of vapor pressure is inversely proportionate to its temperature. It's this really nice sloped line. I've never seen this equation on the AP test, but the kind of fact that it's in our book and all, I just want to kind of introduce it to you and show you what it looks like. Okay, so there it is. I'm not going to ask you to solve this, all right, but it is just a fact that I want you to be aware of, okay? Now, the phase diagram, something that we looked at last year, all right, is kind of an extension of this, and it puts all of our different phases onto one big graph that we can look at. So a phase diagram graphs pressure versus temperature for some substance. It gives you the melting point, the boiling point, the sublimation points at all different pressures, and it also gives you something called the triple point and the critical point. If you cross one of the lines, just before I go on, then you are undergoing a phase change, all right? So let's say you hold pressure constant. Let's say we're right here. All right, this is the ordered pair that we start with. So at this pressure and at this temperature, and let's say a problem says, at what temperature would this substance X melt at if the pressure is held constant? Well, we would say, all right, well, where do I have to take the temperature to? And we'd follow it to the right till we get to the line. When we cross the line, this would be the temperature that it would melt at. All right, so that's how we would kind of navigate this graph. Now, water has a really interesting phase diagram because the critical temperature and the critical pressure are really, really high, like the point at which it becomes a supercritical fluid. And this is because the tremendous amount of intermolecular force of attraction that is present in water molecules. Now, there's something else that's really unusual about water, and that's this line right here. The slope of this line is actually negative. So that means two things. It means that as the pressure is increased, the melting point is actually going to decrease, which is interesting. And it also indicates this, that the solid is less dense than the liquid. And I have seen that on the AP test before, or some AP release stuff that I read through. So make sure you know that. If this line right here has um, a negative slope, that means the solid is less dense than the liquid. That's pretty interesting. The triple point, I think I might have skipped that. The triple point is the point at which the solid, liquid, and gas all exist at the same time. Cyclohexane has a triple point that's pretty easy to manipulate in a lab if you have a vacuum pump. There's some pretty cool videos on YouTube of cyclohexane at the triple point where it just freezes and solids and boils just constantly over and over and over again, which is pretty interesting. Now, if we compare the phase diagram of water to carbon dioxide, the first thing we ought to notice is this line right here, right, is drastically different. And we'll also notice that it cannot exist in the liquid state below 5.11 atmospheres. That's the triple point there, which is kind of interesting. That means that CO2 is going to sublimate at normal pressures. So if you've ever wondered why dry ice just naturally smokes itself away, it's because the triple point of carbon dioxide is at 5.11 atmosphere. So at 1 atmosphere, where we normally are, okay, you don't find any issue traversing this little green line. So at 1 atmosphere, we can sublimate really easily. So that's another, conclusion you might be able to draw from one of these graphs. So pay attention to where the triple point is. Pay attention to where 1 atmosphere of pressure is on one of these, because if you want to know what that substance is going to do at normal pressures, right, 1 atmosphere where we normally live, you can look across and see that. So I know that at normal pressures and at normal temperatures, right, somewhere between, we'll say 0 and 100, that would be normal Celsius. Well, actually, really for human beings, let's say 0 to like 30. So there's about roughly the window of normal things we see every day. We're going to notice that CO2 is a gas, and we're also going to notice that it can sublimate really, really easily. So that's something that we might glean from a phase diagram. Now, the last thing I want to talk about real quick is the liquid crystal and the fact that there is not always an easy transition across that line, or a clean transition, we'll say, across that line. So some substances are not going to translate directly from a solid to a liquid. And they're going to have this little intermediate state, which we call the liquid crystal state. And it's going to have a couple traits of solids. It's going to have a couple traits of liquids. All right. Another way to describe that is just to say that it has some degree of order more than a liquid, but less than a solid. Now, there are 3 descriptors that we use. You can see them right here when we're describing these liquid crystals. And if you look at this first one, this is just normal liquids, right? The crystals in that liquid, or the molecules there, are arranged randomly. If you have a nematic liquid crystal in phase, then the long axis of your crystals are all going to line up. That's it. The ends are not, right? So I can see end here, end there, a little higher. They're not all lined up. If you have smectic liquid crystals, then you're going to get kind of like layers. All right, so I have a layer where all the ends are roughly the same height and the long axis is all still aligned together. And in cholesteric liquid crystals, it looks pretty much like smectic, but I'm on an angle. All right, just like that. Okay, now Liquid crystals, again, probably not something that you're going to see on the AP test, but an interesting little subset of chemistry that they do talk about in your book that I think is worth mentioning. If you do end up going into chemistry later on down the road, you may look at some crystals. When I was in college, I looked at chalcones, which are these little funny shaped molecules. They're kind of like this, and we attempted to get them to stack on each other and in the liquid form in order to get some of this behavior. That was an independent organic chemistry research class that I took. Just something I was interested in. I thought it sounded kind of cool. And then, I saw it in your textbook and I said, hey, those things are kind of similar. That's interesting. So lots of little subsets in chemistry that you might see on down the road, right? So that kind of concludes chapter 11. If you have any questions, let me know, and I'll be glad to give you a hand.